record. Yep. So I'm going to put up a whiteboard so I can give you notes. Yep. So today, we're going to be talking about heat energy, to warm or cool objects. So I'm going to give you the overview. The formula for this one is Q equals MC delta T. We usually say MCAT, although it's MC delta T. So Q is heat energy. You probably know M is mass. C is one you probably don't know. It's the specific heat. And delta T is change in temperature. So we're going to write these all down, then we're going to do a problem or two. So that's the first big skill we're going to pick up today, hopefully. Second big skill is phase changes and heat energy. Heat energy. This formula is Q equals MHL. Q is still heat energy. M is still mass. HL is the latent heat.
Does that say phase?
Phase. Oh, you can't see that very good, can you? Sorry, I'll fix that. Let me get over here more in the middle. Is that better? Sorry about that. So there's two different kinds of latent heat. This is what happens when you do a phase change. So when we do these kind, this is the energy it takes to go from being a solid to a liquid. We call that one fusion. Or from a liquid to a solid. So what's the difference? Well, if I put heat energy in, then I go from solid to liquid. If I take heat energy out, I go from liquid to solid. Okay? And then the last thing we're going to look at are some graphs of these energy changes. Graphs of the energy changes. So lots of things to do today. 1, 2, 3. And I'll wait till everybody's got copied. Let me turn in attendance real quick. Yep, my 4 people were here last period. Yep. I can change that later if I need to. Okay, let's go back to our whiteboard. Okay, here we go. So the best way for me to show you how all these pieces work together is to just do one really long problem. Okay? So here's going to be our really long problem. I did water last time, so let's do something else. Let's do, what material might we want to have liquid something? Okay, so let's go with eraser. We have copper at room temperature we want to change 2 kilograms of copper to 2 kilograms of copper vapor at 1100 degrees Celsius. I'm going to fix that number. I'm hoping that number is big enough. Okay, so room temperature, when AP says room temperature, they mean 20 degrees Celsius. Okay. So this one is not going to have we don't have molten copper, we have solid copper. So the first thing we have to ask ourselves is, what steps do I need to perform to get to vapor copper? We have solid copper, we need it to be vapor copper. So what do we need to do? Okay, so we're going to need to, that's going to be my second step. Phase change from solid to liquid. First thing I got to figure out is, what is the melting point of copper? So let's pull that up real quick. I shall look it up. Melting point of copper in Celsius. Oh, I'm going to have to change my 1100. The the melting point of copper is 1085 degrees. So I have to warm my copper first. I have to warm it up to the melting point, then I have to phase change it. Okay? Just like if I had ice at negative 10 degrees, would ice at negative 10 degrees melt? It would not. So if it wouldn't melt, that means we have to get it up to its melting point, which for water is 0 degrees Celsius. If I have solid copper and I want it to melt, I need to warm it up till it gets to its melting point, which happens to be 1085 degrees. So now I'm going to look up the boiling point of copper, and then we'll put a new number over there. Oh, good. So we're going to change it from solid to liquid. Then our next part of the phase is going to be this. Warm liquid copper to 2562 degrees Celsius. For those of you keeping score at home, it's 1984 degrees Fahrenheit to melt it, which makes it about 3,500 degrees Fahrenheit to boil copper. But that would be cool, right? Like to be able to boil copper off, that'd be kind of cool, I think. And then it'd be a vapor, kind of orangey brown. Don't want to breathe it. Yep, breathing would be bad. So we're going to warm it to its melting point, or to its boiling point, and then we're going to do what to it? Hey, we're going to phase change it again. Now it's going to be a gas. And so let's pick a number bigger than 2562. 2600. Let's go something easy. And then our last step will be to warm gas to 2600 degrees Celsius. This is how they do copper plating, by the way. The energy involved. So last period I did water, and I recorded both sessions, so you can go back and watch the water one. But just to give you an idea, if I have 1 kilogram of water, like one of those quart things of water, ballparky, if I have it as ice, and I want to take it from -2 degrees ice to 102 degrees Celsius vapor, it takes 3 million joules of energy to do that, give or take. To put that in perspective, that would be the same amount of energy as Carter going to McDonald's today and eating a quarter pounder with cheese and a small fries. So the energy to take ice, one kilogram of ice, from -2 degrees Celsius to 102 degrees Celsius is about the same amount of calories you get out of eating a quarter pounder with cheese and a small fry. How many calories do you need? What do they tell you that the average daily consumption should be for humans? For teenage guys, it tends to be higher. For adult men, it's usually around 2,000 calories a day. For adult women, it's usually a little bit less than that. But 2,000 calories, that's a lot of energy. When we talk about food calories compared to joules, that's a lot of energy. And yet, a quarter pounder and a small fries is not going to get you through the day, right? It's not, it might, but it probably won't. You'll be kind of grumbly hungry all day. Yep. So if we do this with copper, let's see how much energy it takes for copper to do basically the same thing. We take copper from solid all the way up to gas. All right, so here we go. Step number 1, I'm going to warm up the copper. So step 1, warming up the copper, is going to look like this. I'm going to erase this real quick, okay? Actually, I'm not. I'm going to just erase a little bit of it. So we can erase the question. Erase the question. So here's step number 1. I do Q equals MC delta T. What was my mass? 2 kilograms. Then this next number is a material property, and the material property is going to be found on page 375 of your book. So specific heats are, just so you know, it's page 375 to get the C values, and it's going to be page 378 to get the latent heats. Okay, so that's where you're going to find those things. 375 is the specific heat. Now, what is specific heat? It's the amount of energy you have to give the material to raise its temperature 1 degree. And everybody has their own. Water is huge, which is why we use water as an insulator for a lot of things, or a coolant for a lot of things. For copper, This number is only 385 joules for each kilogram Kelvin that we do. Q equals MC delta T. All right, now how many degrees do we need to change it? 1085 minus room temperature would be 1065. Kelvin cancels, kilograms cancel. Yeah. Yes, they are. But a change of 1 degree Celsius is equal to a change of 1 Kelvin. Yep. So the good part is, since this is change in temperature, I don't have to change it to Celsius and then subtract them. That would be painful. Okay, so let's do that. 2 times 385 times 1065. 802,050 joules. So that's the heat energy just to get copper from room temperature to its boiling point. So I am going to create at the bottom, we're going to keep a total down here, running total. So the C value, either you're solving for it, or they give it to you in the problem, or they give it to you in the book. In AP, they would give it to you in the problem. Or it would be the thing you don't know and you use the other numbers to find it. Okay? Just by comparison, so you know, the specific heat for water is 2090. So it takes 7 times more energy to warm up water 1 degree than it does copper 1 degree. Which is why you dunk things in water to cool them off and all those things you see people do. Okay, so now that's our first part. I'm going to erase this now. So we've done this step. Now what do we got to do? We now have very warm copper, but it's very warm solid copper. So now what I'm going to do is I'm going to make it change from solid copper to liquid copper. The formula for that is the latent heat one. My mass is 2 kilograms. My latent heat is on page 378. So I flip over there and I go, which latent heat do I use? I use the latent heat for fusion. Sorry, I'm trying to find it. For fusion, because fusion is when we go from liquid to solid, it fuses or it melts. So we use the one for fusion. And just so you know, because it didn't show up over here. All right, latent heat fusion copper. And you'll get a chart like this. And it says the latent heat of fusion. What is their unit, buddy? Okay, their latent heat of copper, 13.1 thousand joules per mole, or 206,000 joules per kilogram. So we need, back to the whiteboard. 206,000 joules per kilogram. I think I can do this math in my head. 12, carry my 1. 2 times 2 is 4. Joules. By the way, this section is called calorimetry. Yes? Say again?
when you write down the formula at the top,
Yep.
there's like a, right?
Yeah. So some books, when you see this, some books will use Q. Some people will write HF. Some books write HL. Heat latent, heat fusion, heat phase change. So you get lots of different ones. Our book uses this one. Yep. You okay with how that formula works? That's a pretty simple formula. Okay? All right. So now what's our next step? Now what do we have?
Warm liquid copper.
We have 2 kilograms of warm liquid copper. All right. And very warm because 1,085 degrees. I would consider that quite warmish. So now we're going to go with what happens on our next step. What are we doing in our next step? We got to make the copper even hotter because we want to boil it. Okay. Which formula do we use for warming or cooling something? MC delta T. So I go back to this equation because I'm changing the temperature. So this is the changing temperature equation. The other one is changing phase equation. So this time we have 2 kilograms. Specific heat of copper, liquid. Let's look at that one. Specific heat copper liquid. Joules per kilogram Kelvin. 390. So the one for solid copper was 385. The one for liquid copper is 390. And how much are we changing the temperature? Oh, we got to get to 2562 from 1085. Then we calculate with our calculator. Because calculators are our friends, mostly. Occasionally they do bad things to us, like pretend to be degrees when they're really radians. Or actually answer the question we asked, not the one we meant to ask. 2060. Oh, wow. 1152060. What do we notice about this number compared to the first time we heated something up? It's a good bit bigger, because what's true about liquids compared to solids in their internal energy? They have more or less? They have more energy hidden inside as heat energy. So that's, you know, how we talk about the heat energy and the motion, that's the piece you have to keep in mind. A liquid will always have more energy than its solid counterpart. Water will be storing more heat energy internally than ice would. Okay, now we got to phase change it. So we go back to, we're going to phase change it, we've got to go back to our Q, and this time we're going to use mass times latent heat of vaporization, which you will also see as QLV, QV, HL. All of those are sort of symbols for the same thing. Mass is 2. Latent heat for copper. Latent heat of vaporization. Copper. Joules per kilogram. Latent heat of vaporization for copper, 4730,000. 4730,000. So 4,730,000. Whoosh. 6. 4 carry my 1, 9. Holy moly. There's our phase change. That's a lot of stinking joules. That is a lot of joules of energy. So, when the United States Mint makes copper coins, are the coins copper all the way through? No. They're zinc, typically on the inside, and then they coat them with copper. How do they coat them? They do not dip them in a little copper bath because that would deposit unevenly and too much copper. Okay? So they spray the copper particles out as charged particles. And they make the zinc the other charge. And then they attract each other, so the copper vapor, that's called electroplating. You ever heard of that? Electroplating is basically the idea that you take charged thing here, charged opposite here, and they attract each other, and then it makes a nice small seal all the way around. So it's a thin layer of copper around. Okay, last but not least, we have to warm the gas. So how do we warm the gas? What formula do we use now? We go back to MC delta T. So we still have 2 kilograms. Let's go with 395. Temperature would be 2600 minus 25. Was it 62?
Yeah.
Okay. I'm going to check that copper one real quick. They don't have it. I'm not able to find it quickly. So we're just going to go a little bit higher than it was for solid. We're just going to add the 5 again. And trust that that's going to put us in the ballpark. So then calculator time. 2 times 395. Let's see, 2600 minus, that'd be 38. 30,020. So our grand total is 12,144,130 joules of energy to do all that. It's the Q total. Now, AP will not have you do all of these in one step. This would not be one part of the problem. They'd have you do part of this, okay? Or talk about the steps. What steps need to happen to solve this problem? To put this into perspective, just to give you a little bit of an idea, because we're not really good with joules, okay? Joules, and we're more familiar with calories, particularly more familiar with food calories, right? So, excuse me. So to give you an idea, this would be 2144, 130. This would be about 2,900 food calories. It wouldn't surprise me if you do. So if the amount of energy your body would need in food would be, let's see, you could go to Red Robin and you could get one of their regular burgers, like All-American Burger or something like that. And you could have a milkshake, because their milkshakes are all between 1,600 and 2,500 calories. So you could have, if you just get a regular burger and a small shake, that would be it. Or you could eat 4 quarter pounders with cheese from McDonald's. Or you could eat, divide that by 45 for me really quick. Yeah, 2,900 divided by 45.
64.4.
You could eat 64 Reese's miniature peanut butter cups. I could totally do that.
I would not do that.
I would throw up probably. It was all over, but I would eat them. I would scarf them down. So Hershey's Kisses, you could probably eat, if it's 64 for the Reese's peanut butter cup, you could probably eat 120 Hershey's Kisses. All right, so what's our big takeaway here? First of all, the calculations depend on what you're trying to do. If you want to warm or cool something, you're using MCAT, MC delta T. If you want to change the state of an object, changing the state requires a heat of fusion or heat of vaporization. What do you notice about those numbers in terms of, here's a temperature change, here's a temperature change, here's a temperature change, here's a temperature change. Here's a phase change and here's a phase change. The phase change at steam is a lot, right? That was a lot of energy to change it from steam, from liquid copper to steam copper. What I want you to understand about that is, if this had been sweat off your skin, the sweat absorbs heat energy from your body and vaporizes. The heat of vaporization for water is 225,000 joules for every 1 kilogram of sweat. So sweating is a very, very efficient cooling process, because water takes a lot of energy to change state, which is why we put it in our radiators. We put it in the cooling tanks around nuclear power plants. It's used as a coolant in a lot of places, because it'll take in a lot of energy, 1, before it starts changing temperature, and 2, before it changes phase. But it's not the best one to use in certain situations. So like in your refrigerator, water freezes at a temperature that's kind of too high, because we want our food in the fridge to be frozen and cold. So we need to go to a lower temperature before the liquid freezes, which is why they usually use an alcohol-based coolant. Yeah.
So would it take the same amount of joules to take a vaporized copper to solid copper?
If you go the other direction, yes. This would be the exact amount of energy that you would remove to get it to go back the other direction. Now, having said that, So the other part here is, what are some other problems they're going to give you? Well, initially you've got these kinds. Just find how much heat energy gets added or how much heat energy gets taken away. The next step, which we're not going to do today, we're going to do the graphs. But we're not going to do the graphs till after lunch because I'm going to let this sit for a little bit. And then we'll do that after lunch. But the second part of this is all called calorimetry. But the second part we're going to do is what happens if I take 25 grams of molten lead and I dump it into a beaker of 100 grams of water. Does the lead solidify? Does all the lead solidify? Does it all solidify and come down to a lower temperature? What's going on? So we'll do problems like one thing loses heat energy and the other gains heat energy, and the transfer is the same for both. So we'll do some of those kinds of problems too, but not today. That'll be Thursday. Okay? So then the last thing we have to do is the graphs. And the graphs are pretty easy, but we will certainly stop here for now and take us a little break.